equation. How do we know what type of ionizing radiation is happening in that equation? What do we look for? If we're given the whole equation, we're given this whole thing. How do we know what type of radiation is happening? We have reactants, we have products. So am I looking on the reactant side or the product side? Get a 50-50 chance. Pick one. Product. We're going to look on the product side. Okay, we have two products. One product is thorium-234. The other product is a helium nucleus. Which one of these two is going to tell me what type of radiation is happening? The helium nucleus, right? Because you could do the math and you could figure out that you were producing a helium nucleus. But in order to know what kind of radiation, you have to find the symbol of the radiation that's being emitted. And in this case, it's a helium nucleus. So if it's a helium nucleus, come up to the top, what type of radiation is happening? Here's my helium nucleus. What type of radiation is happening? Alpha, right? Alpha. So this is alpha radiation. Right? That's the simplest kind of question I could ask about this, right? I'm giving you the reactants, I'm giving you the products. What kind of radiation is happening? All you have to do is look at the radioactive particle that's being emitted. Then you can determine what kind of radiation it is. Okay, so using this equation, compare the reactants versus the products and answer either the same, more in products or more in reactants. So if I look at the total number of protons, let's split this up. Let's look at reactants, let's look at products. If I want to know how many protons are in the reactants, how many do you find? Go up here. Here are my reactants. What number tells me number of protons? 92. 92. That's my atomic number. So if that's true in the reactants, how many are in the products? Go over and look at the same number on the other side. What do you get? 90 plus what? 2, because you have to add them all up. So answer either the same, more in products or more in reactants. So what should my answer be? Should be the same, right? It's just showing you that these nuclear equations balance in a different way than other chemical equations, but they still balance. So how about the number of neutrons? Where do I look for neutrons? Is it the top number? Be careful. Remember that? What is that top number? It's the mass number. What's the mass number? It's really protons plus neutrons, right? So if I want to know my number of neutrons, what do? I subtract 238 minus 92, I get how many? 146, right? Okay, so I have 146 in the reactants. Now I have to do the same thing for the products. 234 minus 90 is what? 144, right? So I get 144 plus these two. What do I get? 146. So what is my answer? It's the same. How about total mass number? Well, total mass number, all I have to do is write that mass number. 238, right? And then 234 plus 4, what do you get? 238. So what are they? The same, right? So that's how we're able to write those equations out when you're just given, you have this and it degrades to that, what kind of radiation was occurring. Okay. So now here's us filling in the blanks, right? Balance the mass numbers and the atomic numbers and provide the correct atomic symbol to complete the equation. What kind of radiation is happening here? So go back to your table, right? And this was the kind of radiation. So what kind of radiation is it? This is beta radiation, okay? So in beta radiation, what's happening here? That's weird. I need to balance to make sure that my atomic number and my mass numbers are the same on either side. So what do? Do the top. I have 131 and I have 0. So what plus 0 is 131? 131, right? Okay, now at the bottom, I have 53 and I have -1. So -1 plus what number gives me 53? Be careful. 54. Same thing as saying 54 minus 1 is 53. So now, how do I know what element that is? Go where? Periodic table, and I go look for 54. What's 54? Xenon, Xe. Yeah? Okay. All right, so what kind of radioactivity? What did we say that was? We said that was beta, right? Okay, so now we've analyzed an equation. We filled in the blanks on an equation. Now you have to write an equation, right? Okay, so provide the nuclear decay equation for the alpha decay. What is alpha? It's my symbol for alpha. 4,2He, right? Because it's a helium nucleus. So a helium nucleus has 2 protons and 2 neutrons. That would give me a mass number of 4 and an atomic number of 2. Okay. So now I'm decaying radium-224. Does that make it a reactant or a product? It's a what? 50-50. It's a reactant. So what you're saying is provide a nuclear decay equation for the alpha decay of radium. That's telling me that radium is decaying, right? So if something is decaying, it started out normally, which is radium-224, and then it decays into something that we have to figure out, right? So half of this is figuring out what's on which side of the equation. Okay, so what's radium? Ra. Radium's Ra. And remember, if you print out your best friend, on the back side of the periodic table, it has all the elements and their symbols, which is really, really helpful. Okay, so 224, does that go on the top or the bottom? On the top. How do I know what goes on the bottom? What is radium? 88. It's in the second column at the bottom. Okay. Now, radium is going to decay into multiple things. One of those things is going to be alpha radiation plus something that we don't know what it is, right? That's our product. So let's put our alpha radiation. We know that. And from this, we can figure out what our other product is going to be. So some number plus 224, I'm sorry, some number plus 4 is 224. So what number do we add to 4? 220. Okay, now down here at the bottom, some number plus 2 gives us 88. 86. So go look on the periodic table. What element has 86 protons? Rn, which is radon instead of radium. Good. Yeah. Okay. Provide a nuclear decay equation for the beta decay of carbon-14. What is beta decay? What's my symbol? E. Okay. Now carbon-14, is this going to be a reactant or a product? Reactant. Okay. Did my screen just stop? Because it now says participants can see the screen. Are y'all able to see all this on Zoom? Oh God, I hope so. Somebody from Zoom, tell me. Yes. Okay, great. Thank you. Thank you. Yay. Okay. I was really worried there for a second. All right. So our reactant is carbon-14. So here's carbon. 14 goes top or bottom? Top. What goes on the bottom? 6. Okay. And then that's my only reactant because it's going to decay into multiple things. So I put my yield sign. And one of the things it decays into is that beta radiation plus something else, right? Kind of gotta do that. So what should be put over here? Let's do the top. What should go on the top? 14, right? Because 14 plus 0 is 14. What goes on the bottom? 7, because 7 plus a -1 or 7 minus 1 is 6. So what element should go here? Nitrogen. Not too bad, right? Y'all got this. Y'all have so got this. Okay. Oh, this is a good one because this is a different type of emission. So carbon-11 is a radioactive source used in PET scans. Y'all know, did we talk about PET scans? It's like they do PET scans, like when they're looking for cancerous spots inside of the body, right? They give you this radioactive source. In this case, it's carbon-11, and they attach it to like a sugar. And y'all know every single cell in your body needs sugar, right? So the cells are going to take in the sugar and use it, and it's going to tag those cells as radioactive. But what do we know about cancer cells? They replicate like this, right? So fast. So how much food do they need compared to every other cell? A ton more. So they pick up a ton more radiation. And then when you scan the whole body for the radiation, then you can see lesions, right? This is when maybe you'd have somebody who had, you can classify their cancer as stage 1, stage 2, stage 3, stage 4, right? Because when you get to stage 4, it's in multiple places in the body. So I try not to knock off my shield, right? But that's how they do that. Okay, things you didn't know you wanted to know, right? You now know that. Okay, so carbon-14 is the carbon-14. Carbon-11 is the source. So is carbon-11 a reactant or a product? Reactant. Reactant. Okay, so put the 11 on top or bottom. On the top, what goes on the bottom? 6, because it doesn't matter what carbon it is, it always has 6 protons. And it's going to decay into a positron and something else. So if you go back to your table, what's a positron? 0 and a +1 at the bottom, and you put the E. So scroll down. 0 and it's a +1, and you put the E. Okay, so now go across the top. What should go on the top? 11. What should go on the bottom? 5, because 5 plus 1 is 6. So what should you have? Boron, right? So you could start out with both carbons, right? But depending on the type of radioactive decay that you have going on, will tell you what kind of other product you're going to make. So that's a really good example. Okay, so this is the last kind of radiation. Now, this is production of radioactive isotopes. Remember we talked about this in class? We said you can produce radioactive isotopes by just streaming neutrons at them. hitting them with neutrons and hoping that the nucleus picks up some of those neutrons, because that's what makes an isotope, right? Is changing the number of neutrons. Well, if you get so many neutrons in there that the atom becomes unstable, then that atom becomes radioactive, starts emitting things to try to get back to that stable point. So this is how they actually make medically relevant radioactive substances, right? So here we have radioactive molybdenum 99, which is produced from molybdenum 98 by this process, provide a nuclear equation. Okay, we have two different substances, and we know we're hitting it with neutrons. Molybdenum 99, is this going to be a reactant or a product? Can be produced, so molybdenum 99 must be a product. So molybdenum 98 is a reactant. Okay, now we have one last thing, these neutrons. Are these neutrons reactants or products? Tell me in words before you do this. How do I make my product, molybdenum 99? You're going to take molybdenum 98 and do what to it? Add neutrons. So should those neutrons be reactants or products? Reactants. Right? Okay, so I'm going to take our reactant, molybdenum. Some people say molybdenum. Some people say molybdenum. I always heard molybdenum, but okay. So what's our symbol? MO. Okay. So if my reactant is molybdenum 98, what goes on the bottom? Look on your periodic table. Look in the transition metals, kind of to the left of the middle. MO should be 42. Okay. Now, I'm adding neutrons. Come up here. When I add neutrons, what symbol do I use? Right? A mass number of 1, but a charge of 0, right? And no protons. Okay. Come down. Okay, so I'm adding neutrons that have a mass of 1 and no protons. What do I get? MO 99. What goes at the bottom? 42. If you're creating an isotope of molybdenum from molybdenum, they have to have the same atomic number because it's the same element. So that kind of helps you to know what this symbol should look like. Okay. All right. So this is just doing the same thing over and over again. So I figure we're okay. All right. Okay. So now, radiation units. Remember in class, I told y'all, if you work with radiation, you have to monitor how much radiation you're getting, right? And just like there are different ways to measure mass, like pounds, kilograms, right? There are different ways to measure radiation. So you could have curies, millicuries, microcuries. There are lots of different ways, and even more than that in the book. But curies is the most common. So when we talk about what's a curie is how many disintegrations, so how many atoms are changing or decaying per second, right? That's a lot. 3.7 times 10 to the 10. That's 10 zeros behind it. That's a lot, okay? So when we talk about treating patients with radiation, we want radiation that is going to decay very, very, very rapidly, right? So it's important that we use the right radioactive isotopes for the right things. If you want to carbon date a rock, do you want it to decay very quickly? No, because by the time you can measure it, right? I want to see what happened to this rock, how old this rock is. Well, if it has a really quick decay time, it's already decayed. It won't give you any information. But do we want things that are very, very still high in radiation to hang out in human bodies when we treat them? No, right? We want it to decay very quickly, get out of their system, and not have any off-target effects. So you'll see different isotopes used for different purposes. All right, so we have a recommended dose of iodine 131 at 4.2. What is this symbol for? Microcuries per kilogram of body weight. How many microcuries of iodine 131 are needed for a 70 kilogram patient with hyperthyroidism? So the thyroid takes up iodine from our diet, basically, that goes into our bloodstream, but then can take in the iodine, which is necessary for the development of certain hormones. So if we're going to treat somebody, right, we can conjugate things to iodine, or we can use radioactive iodine in order to specifically target the thyroid. So the thyroid takes up the radioactive substance and no other body part, right? Okay, so what do? This is just dimensional analysis. So it's another application of dimensional analysis. So I would start with the simplest piece of data, right? We have a 70 kilogram patient, right? But what do I want to eventually get to? Microcuries, right? Do I have a conversion factor inside the problem that gives me that conversion? Yeah, I can go from kilograms to microcuries right there. So what goes on the bottom? Kilograms goes on the bottom, right? And microcuries go on the top. So how many microcuries per kilogram? 4.2. And if there's no number here, right, this is saying the same thing as 4.2 microcuries per kilogram, right? It's the same thing. So you can just put a 1 there. What happens to my units? Kilograms canceled. I'm left with micro, and micro is a U with kind of a long thing on it. Microcuries, 4.20. So what should I get? You have a calculator. What do you get? My second favorite sound in the world is opening calculators. What do you get? 294. That's what I got. 294. Okay. And we're in the right units, so that was it. That was an easy one. All right. And how many sig figs? Do we have sig figs correct? Yeah. 3 sig figs, 3 sig figs, 3 sig figs. Okay. If a patient weighs 175 pounds and there are 2.205 pounds for every 1 kilogram, how much of the radioactive isotope iodine 131 in the above problem will this patient receive? So this time, instead of getting the mass in kilograms, we get the mass in pounds. So you still start out with that weight, but we have to do an additional step first. I need to get rid of pounds and introduce kilograms. So how many kilograms? Right, I need pounds on the bottom, so it cancels, but how many kilograms per how many pounds? 1 kilogram for every 2.205 pounds. But now I'm not where I need to go, because what am I trying to get to? How much of this radioactive isotope I need? So what do? Another conversion, and we're going to use the same dosage that we were given here. Kilograms on the bottom, so they cancel. Microcuries on the top, and it's 4.20 per 1 kilogram. Our kilograms cancel, and we are left in microcuries. So what do you get? And y'all on Zoom could type in what you get, not just asking the people in class. I got 333.33 repeating, right? So how many of those numbers are significant? How many? How many sig figs are here? 3. This is a conversion, so there's an infinite number in a conversion. We don't count that. So really it's just based on this, so it is 3. So you should put 333 microcuries. Okay, and we already talked about disintegration, right? So this is how many times that nucleus emits a radioactive particle and you have this new isotope, right? So it's each time one atom, right, is doing that. So it's disintegrations per second. How many atoms will disintegrate per second into that new isotope? Okay, so how many disintegrations per second are present in a sample containing 2.00 microcuries? Okay, this is a unit conversion problem using information in table 2. So I want to go from microcuries to, what's my goal? Disintegrations per second. So if I come up to the top, I see I have one curie is equal to 3.7 times 10 to the 10 disintegrations per second. So use that. Can I go straight to that conversion though? Because the conversion was, it was 1 curie is equal to 3.7 times 10 to the 10 disintegrations. INT, DISINT, see, even when the word's right there, no problem. Okay, so can I use this right away? Can I just put curies on the bottom? What do I have up here? Microcuries. So that would not cancel. So I need to have microcuries on the bottom, and then what on the top? Just curies, right? So that my microcuries would cancel. So how many curies and how many microcuries? It's okay. So how many curies? Per 1 million. 1, 2, 3. I should have put myself some more space. Right? So where did you get that? That's great. Where'd you get that? From the table. Do they have it in this one? Oh, yeah. So micro, right? Now micro, that's true for anything. You want to go from liter to microliter. You want to go from micrometer to meter, right? It's the same thing. So that 1 million just has to do with the micro. What is milli? 1,000, right? So it doesn't really matter what the base unit is. It's the prefix that we're just concerned with there. Okay, so now I want to get rid of curies and I want disintegrations. Right? So what's my conversion here? Disintegrations per 1 curie. So what do we get? And I always practice these calculations in class because it'll help you on the exam. So what you get? I got 74,000. Is that what y'all got? Yes? No? Yeah, okay. Disintegrations, I'm going to abbreviate. Extend the page. Disintegrations per second, right? Now I'm in the correct units. Good. Y'all think this is helping? Yeah? Okay. All right. I see nodding out in the classroom. I don't know how, I don't know how to see like thumbs up and stuff like that on Zoom. I'm not the best Zoomer. All right, let's see. I think these are really similar to what we just did. So let's go on to half-life. Just like there were extra problems with balancing, it's the same thing with that one. So let's try some half-life stuff. So when we talk about half-life, I always want you to think about those like medical isotopes and the ones that we use in like geology, right? The half-life for something that you're going to give to a person, you want to be a very short half-life. Because what that means is it's the time it takes half of the substance to degrade. So if you have 100 atoms, right, and one half-life elapses, right? If you have 100 atoms, these are radioactive, and one half-life of time passes, LIFE. How many radioactive atoms do you have left? 50. I have 50 radioactive atoms, right? If another half-life passes, how many you got? 25, right? So it's the time it takes. Now, if you're doing carbon-14, that's millions of years, millions of years. Do I want to give a patient a radioactive isotope that has a half-life of millions of years? No, because what's going to happen? They're going to go home, right? They're eventually going to go home. They're going to expose everyone to radiation. Do we want that to happen? No. And eventually they'll die from radiation exposure. So that sucks too, right? Okay, so we want to give them something that has a short half-life of like 30 minutes, 2 hours, something like that, right? 6 hours, so that it clears the body very quickly. Okay, so when we talk about that half-life, that's the pure definition of it. But think about what's going to happen inside of a biological organism, right? We are going to excrete things through urine, through feces, right? So some of that radioactive substance is going to be secreted out of the body regardless of the half-life, right? So if I had 100 radioactive atoms and I set them on the desk and it had a half-life of 1 hour, I would come back 1 hour later and there would only be 50, right? But if I put that inside of a person's body, they would probably urinate some of it out pretty quickly. So I would probably have less than 50 atoms left, and that's the biological half-life. It takes into account not only what the atoms are doing, but also how the body eliminates some of those radioactive particles. So you will have some radioactive particles going into the sewer system. All right, so how do you calculate how much is going to be left after a certain amount of time? Well, we can only calculate based on the real half-life, the what's actually happening with the body, right? And then say, okay, well, it's going to be a little bit faster if we put it in a person. But you can determine that using this formula. Y'all know how to put superscripts into your calculator because you will have to do this for the exam. If you do not know, then you need to Zoom with me and we need to look at calculators and I can show you. But you take, your formula is the isotope remaining, the amount of the isotope remaining is equal to 1/2, and I like to put that in my calculator as 0.5 raised to the n, just because it's easier and you don't have to worry about order of operations, right? Times our starting material, starting amount. Okay, so it's really pretty easy, right? Look, see, carbon-14, thousands of years, right? Radium-226, thousands of years. Uranium-238, billions of years. We do not want to mess with that, right? But look at medicine. Look at our half-lives. 28 days, but you're going to pee out some of it. So really, you're going to eliminate it a little bit more quickly. So that speeds up the half-life. So you go from 28 to 27. Do you see how the effective half-life is a little bit shorter for everything? That's because you're eliminating some of it. Okay. So comment on the size of half-lives of the naturally occurring radioisotopes versus those used in medicine. So tell me about naturally occurring ones. Half-lives are very what? Are very long, right? Versus those used in medicine. Half-lives are what? Are very short. So are radioactive isotopes used in medicine typically naturally occurring? No. What do we do? We make these in the lab, right? Because they are made, right? By bombarding isotopes with neutrons, making unstable isotopes that will degrade very quickly. And we won't find them in nature because they degraded right away, right? Okay. So half-lives are very long. Here, half-lives are very short because they're made. And we want as little, little exposure as possible to our patients. Right? We want it to stay in enough to either treat them or enough to diagnose them, and then we want it out. Because the longer it stays, the longer you have off-target effects and the more harmful it is to the person. Okay, so radioactive iodine 131 has an effective half-life of 7.6 days. So my half-life, 7.6 days. If a dose with an activity of 200 dot, what does that tell me about my sig figs? How many do I have here? 3. I have 3 significant figures here because decimals present. We come in this direction, start counting at your first non-zero number and count them all. So that's the 2 significant, the 0, and the 0 significant. Okay. Is given to a patient today. About how much the dose will remain active after 38 days. So how many half-lives have passed? Well, I'm going to check on this patient 38 days later, right? I need 1 half-life, right, is equal to 7.6 days. So how many half-lives have passed? 38 divided by 7.6. 5? Is that what y'all got? Yeah, okay. So 5 half-lives have passed. So what do I want to do? I know you can solve this 2 ways, right? The formula way and the long way. So let's do the formula way. So what's our formula? So the remaining amount, or however you want to say that, is equal to 0.5 raised to the n, and n is the number of half-lives that have passed, and that is what? 5 times the amount of starting material, which was 200 microcuries. CI, not CU. So what's remaining? I got 6.25 microcuries. Yes? Good. I always like y'all to double check my math. All right, what's the non-formula way? just take your starting material and go through 5 half-lives. So if we start with 200, we go to 1 half-life, what do you get? 100. Go through another half-life. So 1, 2, we get 50. 3 would be 25. 4 would be 12.5. 5 would be 6.25. So either way, you get the same answer. So don't freak out. Okay. We defined half-life already, but let's do the problems. Y'all okay with doing these? Because there weren't very many of them. All right, let's do 2. We have a 120 milligram sample of titanium-99 that's used for a diagnostic test. If titanium-99 has a half-life of 4.8 hours, how much remains 24 hours after injection? So this is the same sort of setup as the last problem we did. What's the first thing that you need to find out? How many half-lives have passed, right? So we know it's 24 hours after injection, but how does 24 hours convert to number of half-lives? So what's a half-life? All right, Fe is 4.8 hours. So my hours cancel. What do we got? It's another 5, right? So now you do that same formula. Your remaining is equal to 0.5 raised to the n times your starting amount, right? So remaining equal to 0.5 raised to the 5 times, we're starting in this case with 120. Make sure you check your units. This one's in milligrams. Okay, so what do you get? Oh, I didn't write down an answer for this. I don't have a calculator, so y'all got to tell me. What do you get? Say it a little louder. 3.75 milligrams. Y'all get that? Yeah, okay, good. All right, so let's do 3. If the amount of radioactive cobalt-60 in a sample decreases, oh, now this is a different way to ask this, decreases from 1.2 grams to 0.3 grams in 30 days, what is the half-life of cobalt-60? If we start with 1.2 grams, right? And over the course of 30 days, we convert to 0.3 grams. This is 30 days, right? How do we find out what 1 half-life is? It's simpler than you think. What happens if I have 1.2 grams of something and it undergoes 1 half-life? What do I get? 0.6. Have I gotten to my endpoint yet? No. So I need to go through a second half-life. What happens when I go through a second half-life? I get 0.3 grams. So how many half-lives have passed in that 30 days? So in 30 days, 2 half-lives have passed, right? So if in 30 days, 2 half-lives have passed, what is 1 half-life? 30 days per 2 half-lives. What is it per, how many days per 1 half-life? Simple, right? So you just have to kind of be thinking in half-life terms. Okay. So how we feel about that? Better? Good? Yay, good. Okay. All right. So what else did y'all say? Y'all said radiation. Let's see. Wait. What are my other two? Hold on. Okay. I have isotopes in general, an atomic mass, and I have unit conversion and dosage calculations. So raise your hand if you want to do unit conversion and dosage calculations, and put a U on the chat if you want unit conversion and dosage calcs, and raise your hand if you're in the classroom if you want to do this one. Yeah. Oh, we got a lot on Zoom. Okay, so then, because we're probably only gonna be able to do one more. Then on the chat, put an I if you want to do isotopes and atomic mass, and raise your hand if you're in the classroom and you want to do it. I could probably make a video where I go through it. Yeah, sure. Okay, so I don't think anybody in either place wanted to do isotopes and atomic mass. So let's do this. All right, so we have 20 minutes about. So the part one is basic dimensional analysis, putting up your fence posts. And then part two is really dosage calculation. I kind of feel like we should skip to dosage calculations. Y'all okay with that? Okay, if anybody's not okay with that on the chat, write no. Okay. All right. So, and y'all know the prefixes are there, right? You have the prefixes. You don't need to memorize them. The common equivalence is on your best friend, right? You don't have to remember that. Okay, so let's see. I don't remember if there was some here. Oh, no. That was just an example. Okay, so our very first one on dosage calcs. All right. Whenever you're doing this, the number one thing that people get in trouble with is that you don't keep track of your units. When you do this, keep track of your units. Never put something into a dimensional analysis that does not have units. So here we go. Let me move this down here. So a visitor from Europe knows their weight to be 75.2 kilograms. How much does this person weigh in pounds? This one's really easy. This is what we already kind of did, right? Always remember that whatever you want to get rid of, you put on the bottom, and whatever you want to introduce, that's not true. I need to not say that. Whatever unit you want to get rid of in the new conversion factor that you're going to put on your fence posts, what you want to get rid of has to be in the opposite location of where it is. So if kilograms is in the top and you want to get rid of it, kilograms need to be on the bottom. But sometimes you're going to have something on the bottom, and to get rid of it, where would you have to have it? On the top, right? Okay. Try to say that without being too confusing. All right, so kilograms goes on the bottom. So what am I trying to get to? Pounds. So what's my conversion? I know that 1 kilogram is equal to 2.205 pounds, right? Where did I get that? See, some people are like, here, right? Also on the best friend. It's in both places. Okay, so that puts, I put the 1 with the kilogram, I put the 2.205. So what do you get? I'm going to get, let me check my math. I get 165 pounds, right? I don't know how I'm doing that. 165, is that what y'all get? Okay. All right, a friend of yours is running a 10-kilometer race. How many miles is he or she running? I want to get rid of kilometers. So kilometers goes Bottom, what's my conversion? I know in 1 kilometer, I have, look on your table, 0.62 miles. Yes. Yes, but this would only give you a 1 sig fig, right? Did we not do sig figs on the other one? 0.62, 0.620. This would be 3 sig figs because this is 3 sig figs. You never take a conversion factor into account when you're looking at sig figs. So if this is, oh, I was writing on the conversion factor. This is 3 sig figs. So this is 3 sig figs. Yeah, I was writing on this. Okay. So here, really, what is our final answer going to be? Only 1 sig fig. So I put 1 kilometer per 0.62 miles. What do I get? Just move your decimal place 1 time. 6.2 miles. Yes. And really this rounds to 6. But now if they put a 10 kilometer race, that would be 2. Yeah. All right. And this one, I'm going to put a dot on it. A mother is to give her child 10 cc's of medicine every 4 hours. Unfortunately, she lost the syringe. Y'all don't know how many times that happens. It does happen. Which measured cc's that came with the medicine. She calls the clinic for help. How much medicine can you instruct her to give the child? So start with what you know, 10 cc's. What does she probably have at home? She doesn't have a syringe. She has what? She has a spoon. She has a teaspoon or a tablespoon, right? So usually kids, you're probably going to calculate teaspoons. Okay, so let's go to teaspoons. So teaspoons is going to be our goal. This question didn't tell you that explicitly, but we're going to assume that they have a teaspoon at home. Okay, so I need to convert from cc's to teaspoons. Look on your table up above or on your best friend. Do you have a conversion straight from cc's to teaspoons? No, you don't. So we're going to have 2 conversion factors, at least 2 conversion factors. So what do you have that has teaspoons in it? Milliliters. What's your conversion? 1 teaspoon is equal to 5 milliliters. Okay. That means that in order to get to teaspoons as our goal, we're going to first have to get rid of cc's and go to milliliters. Do we have a conversion for that? Yes. What's the conversion? 1 milliliter is equal to 1 cc. It's the definition of a cc. Okay. So now I put in my next conversion. My cc's cancel. I'm in milliliters. So I put milliliters on the bottom, teaspoons on the top. 5 milliliters, 1 teaspoon. Milliliters cancel. What do I get? All 1. So 10 divided by 5 is 2. 2 teaspoons. So what do you tell the mom? Give your child 2 teaspoons every 4 hours. Every 4 hours. That's kind of a good thing to know, right? Even as a parent, just in general, or as a patient in general, right? If you lose the syringe, you know you can convert the dosage. Okay, here's a better one. A physician orders a dose of 250 milligrams of the antibiotic, and I don't know how that's exactly pronounced, 3 times a day. The medicine is available suspended in a liquid as, I'm going to suggest, when you're looking at these, anytime you see an equivalent relationship, you write it out. So I see 125 milligrams per 5 mils. So that's 120 milligrams for every 5 milliliters, right? For this problem, okay? The dosage is 250 milligrams of the antibiotic 3 times a day. So what is that? What kind of a relationship can I say with that? You're going to have 3 doses per day, right? Yeah. So 3 times a day is a dose, right? So this is 250 milligrams of the antibiotic 3 times a day. So that's 250 milligrams per dose. They don't explicitly say those things in dosage calculations, but it is a dosage calculation. So you need to be thinking about dosage. Okay, the patient only has a teaspoon available for administering the medicine. How many teaspoons will the patient need to take each dose? Well, if we can convert it to milliliters, then we know from the last problem, right? We can go from milliliters to teaspoons. So let's calculate it in milliliters, and then we'll just convert it to teaspoons. Okay, so what do we start with? Let's do for how many teaspoons will the patient need to take each dose? So for 1 dose, what do we do? What do we start with? 250 milligrams per dose. So in this problem, I'm never going to get rid of dose, right? I'm going to want that to stay. So what do I have to get rid of? Milligrams. Do I have something up at the top that will allow me to do that? Yeah. What have I got? So in 5 milliliters, I have 125 milligrams. Now I'm in milliliters. If I want to get rid of milliliters, what am I going to use? I know there are 5 milliliters in 1 teaspoon from the last problem, right? So what goes in front of teaspoons? 1. What goes in front of milliliters? 5. Okay, so what are my units currently? Milligrams canceled, milliliters canceled. I'm left with teaspoons per dose. Is that what the question's asking me for? How many teaspoons will the patient need to take each dose? Yes. So what do you get? I got 2 teaspoons per dose. Did y'all get that? Now, this is a really good, I really like these problems. You want to know why? Because I'm crazy. But the other reason is because you know the answer is not going to be like 500 teaspoons, right? So if you end up like multiplying things you weren't supposed to multiply by and you get like 1,000 teaspoons, you did the math wrong, right? So it's a really good red flag for you to go back and say, whoa, I did something wrong, right? So these logically have to have a right answer. Like if you're solving for tablets and it says that you need to give a child 80 tablets. I don't think so. I really don't think so. So it's good because you kind of know what you should be getting. All right, but that's not all we need to know. We also need to know each day. So in 1 day, what are we going to do? Well, I'm going to take my answer here, right? I already know that he needs to take 2 teaspoons per dose. Do I have a conversion factor up here where I can convert? Now I want to keep my teaspoons. I want to convert dose to days. Can I do that? Yeah. I know here I have 3 doses per day. Do you see how easy it was to go back to all the stuff we had written at the top rather than have to reread the paragraph 6 times? That's a good thing to do. It kind of sucks if you forget something, if you miss something, but if you don't find what you're looking for, go back and reread the question again and see if you can pull out another piece of data. Okay, so we need 3 doses per day. So doses doses cancel. What does he need in a day? 60 cents per day. All right. And then you know how much medicine overall to give to the patient, or how much you'll need to treat the patient for a day, or whatever it is. Okay. The other kind of dosage calculations were ones that had drip rates for IVs. Remember those? Okay. So in this one, we have a patient that gets 2 liters of dextrose 4%. What's dextrose? It's a sugar, right? In a 0.18% sodium chloride. What is sodium chloride? Salt. Why do we want to give the patient salt? We'll talk about this when we talk about osmosis, but you have salt inside of you all the time, right? You have it in your bloodstream, and that's where this IV is going, to your bloodstream. So you have to make sure that the salt content in the blood is exactly the same as the salt content in the IV, or you will severely harm your patient. So a saline solution is not just water, right? It's salt water, because your blood is partially salt water. Okay, over 18 hours through an IV. So what information do you think we're going to need in that one sentence? What can you pull out? In the first sentence. They get 2 liters. Is there another part to that? Over 18 hours. My goal is to calculate the drip rate in drops per minute. So my goal is GTT, remember that, per minute. Or drops per minute, however you want to, doesn't matter. The IV delivers 20 drops per milliliter. So I know I have 20 drops per milliliter, and you could put drops. You could just do that. Then it's easier. Okay, so what do we start with? Doesn't matter. Pick either one of these 2 things. Does not matter. Let's do 20 drops per milliliter. I'm trying to go from drops per milliliter to drops per minute. So do I need to change the drops? No. Do I need to change the minutes? I'm sorry, the milliliters. Yes. I want to get 2 minutes. So milliliters is on the bottom. Where's milliliters going to go? Top. Okay. Now what? We use this one, we can't use it. Now I need to go to liters. I need to go to liters because my next conversion factor has liters. So I can't stay in milliliters. I need to change. So do I have a conversion for that? Not in the problem, but your best friend does. What does your best friend say? 1,000 milliliters in 1 liter. Now milliliters cancel. I have drops per liter, but that's not what I want. What do I want? Drops per minute. I don't have a conversion factor that has minutes in it, but I do have one that has liters. So let's use that. So I want to get rid of liters. Liters is on the bottom, so I'm going to put liters on the top. 18 hours on the bottom, so 2 liters in 18 hours. Am I done? No, because I want to get to drops per minute. And now I'm in drops per hour. So I want to get rid of hours and I want to get to minutes. Do y'all know something that can help me? How many minutes in an hour? 60 minutes in 1 hour. Now, let's make sure my liters have canceled, my hours have canceled. I'm in drops per minute. Yes. So what do you get? What do you got? 37 drops, yes, per minute. Now, how many sig figs? Really, it should be what? I'm only counting one. I use the 2 here, that's 1 sig fig. The 18 here, that's 2, and then the 20 here has 1 sig fig. So really this should be 40 drops per minute. Yeah. Okay. There are more problems, but I think we're getting close to the end. So has this been helpful? Yes. Okay, I will post the recording of this. I will go back and pick up, which one didn't we do? The isotopes? Yeah, I'll go back and see what I can do in the next like 24 hours. I'll do my best to give y'all something on that. Sound good? All right, if y'all need anything, please email me, you know, and I will help you out. If you get to exam time and you start to struggle, you have problems, please email me. Okay, do not struggle and get frustrated and get upset. Just call me, email me. We'll get it fixed. We'll get it figured out. Okay. All right, y'all have a great weekend. It was so good to see some smiling faces, and thank you for being on Zoom. Y'all are free to go. Anybody on Zoom need anything else? Does not look like it. Okay. Yep, once everybody leaves Zoom, then I'll shut it down. Ari, you got something you need to ask? I want to close the Zoom unless if somebody has a question.